The next topic that we're going to be discussing is called Hess's Law. And Hess's Law is just looking at these reactions that we've been looking at, these thermochemical equations, but we're going to look a little bit more in depth because we're going to see that not always, kind of like that last example, are we dealing with 1 mole of something or 2 moles of something. We might have, a half of a mole or 0.234 moles. I mean, it's not perfectly 1 mole. So when a reaction is multiplied by any kind of a factor, that delta H of the reaction is also multiplied by that factor. Delta H of the reaction is extensive. That means that it depends on the quantity being used in that. It depends on the mass that's being used in that reaction. So let's look at the example of the diamond that we talked about previously. You have carbon in solid form, combusts with oxygen to create carbon dioxide gas. And the exothermic energy released is negative 393.5 kilojoules. Now, let's say that I had 2 moles of carbon, so I doubled everything. I had 2 moles of carbon, 1 to 2 moles of oxygen, and 2 moles of carbon dioxide gas were released. Notice that my delta H is then just multiplied by 2. So then this exothermic reaction, there is double the energy that is being produced because we multiplied everything by 2. It could be by 3. It could be, we could have it. If I said half of this oxygen, half of everything, I would take half of my delta H. Similarly, if the reaction is reversed, then the sign of the delta H is changed. So let's say I took this, notice that with my carbon plus oxygen to get CO2, what if I flipped this around and I made it a decomposition reaction instead of a synthesis? I'm decomposing and breaking that bond. So I have CO2 as a reactant and my carbon and oxygen are products. All we do is we flip the sign to my delta H. It was an exothermic reaction, but when you flip it around, it becomes an endothermic reaction. All we did was change the sign. Then, continuing, so Hess's law says the change in enthalpy for a stepwise process is the sum of the enthalpy changes of the steps. So, if a reaction can be expressed as a series of steps, the delta H for the overall reaction is the sum of the heats of reaction for each step. So if we were to look at this and say, okay, so delta H for number 3 is the sum of number 1 and number 2. So let's look at number 1. Let's say that first this reaction happens, second this reaction happens. So my delta H3 is taking delta H1 plus delta H2 to get my overall delta H of the reaction. Let's see if we can model an example of Hess's law. This is telling us that it's giving us this information. There are 3 elementary reactions that it's telling us. It says that 2 moles of NO gas plus 1 mole of oxygen gas create 2 moles of NO2. And that is an exothermic reaction that produces 116 kilojoules of heat. Element reaction number 2 says that 2 moles of N2 gas plus 5 moles of oxygen gas plus 2 moles of water create 4 moles of HNO3. Again, it's also an exothermic reaction, produces 256 kilojoules of heat. And the third elementary reaction says that 1 mole of nitrogen gas plus 1 mole of oxygen gas creates 2 moles of NO. It's an endothermic reaction and absorbs 183 kilojoules of heat. So this is telling us it wants us to calculate the delta H for the reaction below using these 3 elementary reactions to make this target reaction. So where we're going to start is by no reason, because it's other than it's just listed first, we need to figure out how to simplify these three target reactions into the target reaction. And you know how you can simplify it in algebra, like if I had a 2x on one side of the equation and a 2x on the other side of the equation, that they would cancel out, right? Because we would subtract 2x from both sides. So 2x minus 2x gives us zippo. So we need to figure out how to arrange these elementary reactions so that we get this target reaction. So let's look at how, we want to look and see where do we see NO2 in one of these elementary reactions. NO2, NO2, it's not in the third one, and there's no NO2 in the second one. There is an NO2 right here in this first elementary reaction. But if you notice, this NO2 in the elementary reaction is on the right side of the equation, and I want it to be on the left side. So we need to flip this first elementary reaction, flip it so that this is on the other side. So I'm just going to draw an arrow here telling us that we need to flip this first one. And remember, if we flip, we also need to change the sign on our delta H. So we're going to make it a plus. Also, notice that this is 2 moles of NO2 and I want 3 moles of NO2. So how do I go from 2 to 3? Well, what can I multiply 2 by to get to 3? If I multiplied it by, let's just make it easy and say 3/2, right? Because 3 times 2 would be 6. 6 divided by 2 is 3. So again, if I do that, that would give me 3, but I have to do it to every piece in that elementary reaction. So let's just rewrite elementary reaction number 1 with these modifications that we just did. So we're flipping it, so we're going to start, since this was our product, we're going to start over here as a reactant. And we are making this 3NO2 with an arrow. 3/2 times 2, again, gives us 3NO plus, we're just going to say 3/2 O2. And that delta H is 1. I need to multiply my delta H by 3/2. So let's do 116 times 3 divided by 2. So my delta H is plus 174 kilojoules. Remember, whatever we do to the 1, we have to do it to all of the pieces of that elementary reaction. Okay, so we have the first part of our target equation done. Now, let's see where we can find H2O. Not in the first elementary reaction. And, oh, it's right there. And what's great is this H2O is a reactant. And over here, this is a reactant, which is great. We don't need to flip it. But what do we see? We want 1 mole of H2O, and right here is 2 moles of H2O. So how do I go from 2 to 1? Well, let's cut it in half. All right, so we just need to take everything in this equation and cut it in half, even our delta H. Okay, so let's rewrite elementary reaction number 2 with everything cut in half. So half of 2 N2s is 1 N2. Half of 5, let's just say 5/2 of O2, plus half of 2 waters is 1 water. Half of 4 would be 2 HNO3. And then delta H, if we cut that in half, would be 256 divided by 2. It's still negative. We didn't flip the sign, so it's negative 128. Okay, so we've got this good, we've got that good. Now, do we have 2 moles of HNO3 on the right? Yeah, we do actually at this point. That's great. Do we have NO on the right? Good. But do I have, I only want 1 mole of NO, and right now I have 3 moles of NO on the right. So I need to figure out how that can simplify, right? Because I can't mess with that anymore. So let's look back at our elementary reactions and go, ooh, 2 moles of NO is in this reaction. If I were to flip this one and have 2 NOs on the left, 3 NOs minus 2 NOs would simplify down to 1 NO. So let's look at number 3. Let's just flip number 3. So I would have 2 NOs, N2 plus O2. So my delta H is flipped, negative 183. Now let's look to see what we have. I have 3 NO2s, which is great. 3 NO2s. Now there's a lot of other things I've got going on, but if we look, we've got my H2O. Yep, I've got H2O right here. But I've got some other things happening. So let's pause, because I don't want nitrogen on the left, right? That's not in my target equation. But if I look, I have a nitrogen on the left of the arrow and a nitrogen on the right of the arrow. So those cancel out. Notice I also have oxygen. There's not oxygen in my target, so let's see what happens here with these oxygens. I've got 5 halves oxygen on the left. I've got a 3 halves oxygen, and I have 1 oxygen, but 1 is the same as, let's write 2 over 2, right? That means 1. So 3 halves plus 2 halves is 5 halves. So really, I can combine these 2 oxygens on the right. 5 halves cancels my 5 halves out. Okay, and then we can look at these NOs. On the right I have 3 NOs, on the left I have 2. So this 2 NOs is canceled, and that cancels that 3 down to 1. Now, let's see what we're left with. 1 NO, and I'm just going to write it in the same as this. Do I have 2 HNO3s? I have 2 HNO3s. Plus my 1 NO. So because I got this target equation, now all I need to do is add up my delta H's. So I'm going to do 174 plus negative 128 plus negative 183. And I get a delta H of negative 137. So that tells me that this reaction is an exothermic reaction, and the total exothermic reaction, the delta H of the reaction is negative 137 joules. Let's look at another one. So we're given 2 elementary reactions. The first one is copper plus diatomic chlorine to give us copper 2 chloride. This, with a exothermic reaction. And on the second one, we have 2 coppers plus diatomic chlorine to give us 2 copper 1 chlorides. And we can see that that's an exothermic reaction as well. Here's our target reaction that we want to create, Cu plus the copper 2 chloride to give us 2 copper 1 chlorides. So let's figure out what the heat of that reaction is. So if we were to just start with our first copper in solid form and look and see where is that unique in our elementary reactions. we could look and go, oh, it's in number 1 on the left and it's in number 2 on the left. So it isn't in a unique spot. So let's hop over to our next one, just so we can build off of somewhere. CuCl2, where is that? Again, if I look, not this guy, oh, it's right here. So in this elementary reaction, the CuCl2 is on the right side of the arrow, and we want it to be on the left. But luckily, our moles are 1 and 1. So all we need to do is flip this first reaction. So let's do that and write CuCl2 on the left, Cu plus Cl2, and then that delta H, all we have to do is flip the sign. So it's 206 kilojoules. Okay, so that gives us our CuCl2 on the left. And then on the right, after the arrow, we need 2 CuCls. So let's find where that is in our elementary reactions. And if we go, oh, look right there, that CuCl is the right mole ratio and it's on the right. So wow, that is pretty great. It doesn't happen very often where we don't have to do anything to that second one. So let's write 2 Cu plus Cl2 yields 2 CuCl. And the delta H stays the same because we didn't do anything to it, negative 36 kilojoules. So let's see if that solves what we needed. I've got my CuCl2 on the left, which is good. I'm going to write CuCl2. Oh, Cl on the left. We're going to pause and see what else we can do that's nice. Like this too, CuCl. That's great. Let's write this down. 2 CuCl. That's the only thing I want on the right. So everything else we need to cancel out. Let's see if that works. Well, we've got a Cl2 on the left and a Cl2 on the right. So yes, those cancel. And we have 2 coppers on the left and 1 copper on the right. So they're not going to cancel, but this 1 copper will make that 2 coppers down to 1. And thank goodness, because that's all we wanted down here was 1 copper. So good. Now all we need to do is just add up these delta H's. Oops, sorry. Where I just need to do 206, positive 206, plus a negative 36. And our delta H for the reaction is positive 170 kilojoules. So this has become an endothermic reaction. The next topic we're going to talk about is standard conditions. So the standard state is the state of a material at a defined set of conditions. So for example, pure gas is at exactly 1 atmosphere pressure in its standard state. A solid or a liquid in its most stable form at exactly 1 atmosphere pressure and temperature. And that temperature is usually at room temperature, which is defined as 25 degrees. 1 atmosphere pressure, if you remember from the gas laws unit, is also equal to 760 millimeters of mercury. It's also equal to 101.3 kilopascals, which is the metric unit. But it's just telling us that at a standard state for any of these reactions happening, so it's not an extreme condition. This is being able to replicate any compound or formation of any of these reactions at these standard conditions. Also, standard condition for a substance in a solution with a concentration of 1 mole, which is 1 moles per liter. There's also the standard enthalpy change, which is delta H with this not sign. It's the enthalpy change when all reactants and products are in their standard states. So it's just clarifying. Then we have the standard enthalpy of formation, which is delta H naught with a sub F for formation. It's the enthalpy change for the reaction forming 1 mole of a pure compound from its constituent elements. And constituent elements just means what the compound is made up of. So for example, if I said carbon plus oxygen to create CO2. So the constituent elements making up carbon dioxide in its standard state, in its pure form, we have carbon and we have oxygen. Oxygen, remember, by itself in its pure natural state is diatomic, O2. So what this is also telling us is that the delta HF, the heat standard enthalpy of formation for a pure element in its standard state is, by definition, 0 kilojoules per mole. We don't form elements. Elements are found naturally. We don't form elements. We form compounds made up of those elements. So these individual elements found in their natural standard state have a value of 0 kilojoules per mole. Here we have a table that's our standard enthalpies of formation, and we can look at this and it's going to be a huge reference, but as we can see, let's look at bromine, for example. Bromine in its natural state is a diatomic molecule and it's in liquid form, Br2. That's part of Brinkelhoff, part of that lucky 7 found naturally is a diatomic form. And we can see, remember that last definition, the heat of formation is 0 because we're not forming that. However, to make bromine, to turn that liquid form into a gas, we can see requires heat energy, 111.9. We can see to form the compound HBr is an exothermic reaction, and the heat of formation is negative 36.3. Calcium, found as a solid on the periodic table, again, by definition, calcium as natural is 0, but to form these two different compounds, we can see the heat of formation and what that is. Carbon, as a solid found in its natural state, is graphite. Again, we can see that its heat of formation is 0, but obviously to make carbon into a diamond requires energy to be applied, and we can see that heat of formation. And again, you can see with all of these different compounds of carbon, we can see what that heat of formation is for those compounds. And you can go on and see for chlorine. Again, chlorine, diatomic chlorine is its natural state, its heat of formation 0 because it's an element. To get rid of one of those chlorines, to break that bond, we can see requires energy. And we can see all of these kind of in alphabetical order to use for reference for the standard enthalpies of formation. So reactions of elements in their standard state to form 1 mole of a pure compound. If you're not sure what the standard state of an element is, you can find the form in Appendix 2B at the back of your book that all have those delta H of formations that are 0. The one that we used just right before here was table 6.5, if you can also find that, but there should be a pretty extensive list. So the definition requires 1 mole of compound to be made. The coefficients of the reactants may be fractions. And an example of this could be, suppose I wanted to make carbon monoxide. I want to make 1 mole of this compound to be made, CO. That means that, well, what makes up carbon monoxide? Well, carbon does and oxygen does. And we know that this is how they are found. Carbon is just C and oxygen is O2. Well, C plus O2 is not carbon monoxide. So I can have a half. This is what that's telling me. Coefficients of the reactants may be fractions. I can have half of an O2 to form 1 mole of that carbon monoxide. And this just kind of reiterates, if we were to write the formation reaction for carbon monoxide, we can't just write C plus O to give me CO. It doesn't happen because the elements must be in their standard state. So if I look at standard state, and again, if you're not sure which is standard state, you can use this table. We get what makes up carbon monoxide? Well, carbon does. So we would look at carbon and we would say, okay, which one of these carbons is in its natural state? The one with 0 heat of formation. So it has to be this one, the carbon. This is a solid graphite. So carbon, solid graphite. The other one, the other element made up in this compound, oxygen, we would look up oxygen, oxygen, and there's 2 oxygens given. How do we know which one? It's the one with 0 heat of formation, so O2, so molecular oxygen. Then we need to make sure that the equation must be balanced, but the product compound has to only have 1 mole, because if I looked at this and wanted to balance it, our first reaction is to go, oh, I have 2 oxygens on the left, let's have 2 on the right. Oh, now I have 2 carbons, let's have 2 carbons on the left. That is also balanced, but doing these rules, our final resulting compound has to be 1. So I can't just throw that out there. I need to have half of an O2. So use whatever coefficient in front of the reactants is necessary to make the atoms on both sides equal without changing the product coefficient. This is 1 mole of carbon monoxide. Let's look at a couple examples. We're going to write the formation reactions for the following: carbon dioxide. So we're going to look at carbon. Well, what makes up carbon dioxide? Carbon and oxygen. So we're going to find carbon in its natural state. Again, looking here, which one is 0? So it's carbon, solid graphite. And we know that that is a 0 heat of formation. And oxygen, again, if I wasn't sure if it was O2, I'm going to look up oxygen, find the 0 heat of formation. It's O2, diatomic oxygen. And to create CO2, I can simply, and just look it up, CO2 heat of formation is negative 393.5. So I can say that this thermochemical equation has a exothermic negative 393.5 kilojoules per mole. Formed 1 mole of CO2 formed from its constituent elements, carbon and oxygen. Another example we can look at is aluminum sulfate. So again, we need to look up what elements make up aluminum sulfate. So we need to go, okay, aluminum, and aluminum is found in its natural state as just Al, aluminum. We need to look up sulfur, and we need to look up oxygen. So sulfur, if I look on here, sulfur, again, which one is 0? So sulfur in its natural state is S8. It's a rhombic. So I've got my S8 rhombic, which would, again, is 0 heat of formation. Aluminum, there we go, aluminum in solid form is 0. And oxygen, we know, hopefully you're starting to learn that O2 is oxygen's natural state. So these are my 3, what make it up, and then you can simply look up in the appendix or in the larger, this one doesn't have my aluminum sulfate, but it would be on the other chart, the heat of formation for aluminum sulfate. And you can see here that all of these combine to create 1 mole of aluminum sulfate. So because aluminum sulfate has Al2, that's why I have 2 aluminums on the left. It's a balanced equation. Notice that I have 12 oxygens, so I have a 6 right here. I have 3 sulfurs, but remember my sulfur in natural state is S8. So that's why I have a fraction here. 3/8 will get me that 3 sulfurs for my product. So we can calculate the standard enthalpy change of a reaction a couple different ways. Any reaction can be written as the sum of formation reactions, or the reverse of formation reactions for the reactants and products. And we did that with Hess's law when we were doing our elementary reactions to find our target reaction. We can also do it we can also find the delta H for the reaction as this, this is part of it. We then find it by the sum of those delta H F's for the component reaction. So this was one way, this is what we were just doing all of that practice. But the other way we can do it is by finding these heat of formations for our products and subtracting the heat of formation from the reactants. So we're summing all of the heats of formations for the products and subtracting it from all of the reactants. And N is this coefficient of the reaction. So I'll show you what that means here in just a second. Let's do a practice problem. So it is important to make sure that we have a balanced equation, and this one was not. So there is 2 here in front. CH4 methane plus 2 oxygens yields CO2 and 2 waters. So we need to use this standard enthalpies of formation here. And I'm going to just simply look these up. CH4, I'm going to find its delta H, its standard enthalpy of formation is negative 74.6. We're going to look up our oxygen, which hopefully you're starting to realize, oxygen. Oh, that O2 is 0 because that's in its standard state. Now, there are 2 oxygens, so we do need to do 2 times 0, but that's still going to be 0. Carbon dioxide, let's look up that heat of formation. CO2 in gas form is negative 393.5. And water, let's look up H2O. H2O, is it liquid? Oh, it's gas. H2O is negative 241.8. And there's 2 of them because we had to balance that equation, so we need to multiply that by 2. So now we just need to do some math because remember we learned that delta H for the reaction, for this reaction to happen, we could look up that heat of formation by summing, sorry, that's not a very nice Greek symbol of summation, summing the products minus the sum of the reactants. Okay, so let's do our products first. Let's add these up. So I have negative 393.5, and I'm going to add the product of this. So let's do that. So I'm going to do 2 times negative 241.8, and I'm going to add negative 393.5. So for my products, the right side of the equation is my products. My products, I got negative 877.1. And then I'm going to subtract my reactants sum. And again, 2 times 0 is 0. So my reactants is negative 74.6. Then when I do that, I've got my sum of my products, which was right there, minus the sum of my reactants, which is right there. So now let's do negative 877.1 minus a negative 74.6. And there we go. Our heat of formation for this whole reaction is negative 802.5 kilojoules. Again, all I did was look at my standard enthalpies of formation chart for each reactant, for each product. If there was any coefficients, I had to distribute that in. And then I did my products minus the reactants. Let's do another practice problem. I'm going to calculate the enthalpy change in this reaction. So we have C2H2. Again, I'm going to look on my chart. C2H2 has a enthalpy heat of formation of 227.4. And again, there's 2 of that, so I'm going to make sure to multiply that by 2. Remember, oxygen, O2, standard state, so it is 0. Again, you could look that up also. Those are my reactants. Reactants. Let's look at my products. CO2 gas, standard heat of formation is negative 393.5. And that has a coefficient of 4. And then liquid water, H2O, liquid water is negative 285.8. And we need to multiply that by 2. Okay, so I'm done with my chart here. Now I just need to do the combining of find the heat of the reaction. I need to do my products. So let's do 4 times negative 393.5 plus 2 times negative 285.8. I'm going to do that first, and I'm going to subtract my reactants, which is going to be 2 times 227.4. Okay, let's plug this in. And you should get a heat of reaction for the reaction is negative 2,600.4 kilojoules of heat. Again, we're doing products minus reactants, and we're getting these numbers right from that chart, the standard enthalpies of formation. Let's look at another example. It wants to know how many kilograms of octane must be combusted to supply 1.0 times 10 to the 11th kilojoules of energy. Okay, so first, let's write this reaction out. Octane is C8, and it's an ane, so it's times 2 plus 2. So 8 times 2 is 16, 17, 18. C8H18. Plus, if it's combusted, we know that oxygen is added. And we know combustion results in CO2 and H2O. So next we need to balance this. Got 8 carbons here, so let's try having 8 carbons over here. I've got 18 hydrogens, so let's try a 9 times 2 is 18 there. And then this would give me 16 plus 9, so that's 25 oxygens. Can't do 25, that's an odd number, so let's just do this, 25 halves. We'll cheat a little bit because when I go through and look at these standard enthalpies of formation, oxygen is a 0 anyways, right? Because it's standard state, so it doesn't matter what that fraction is in front of it. It's going to be the same. Okay, now, we don't know what this octane is because we want to figure out how many kilograms. I mean, we don't know. Yes, we're going to find this out. But let's look up the standard heat of formations for everything else. So our CO2 gas is negative 393.5. And we're going to multiply that by 8. And my H2O is negative 241.8, and we're going to need to multiply that by 9. And I forgot to finish my thermochemical equation here. My delta H here is 1.0 times 10 to the 11th kilojoules of energy. So let's write this out. We know before the last couple ones we've tried to find my delta H. I know my delta H for the reaction is 1.0 times 10 to the 11th kilojoules. I also know my products and I can subtract my reactants. So let's start writing this. We're going to do 8 times negative 393.5 plus 9 times negative 241.8 and subtracting our reactants. So because this is 0, 0 plus, we'll call this x. We can say just minus x. All right, let's simplify this. We should get negative 5,324.2. So we've got 1.0 times 10 to the 11th kilojoules is that minus x. Well, let's do some algebra here. Let's add 5,324.2 to both sides to get rid of that. 5,324.2. So if I do this on my calculator, 1E11 plus 5,324.2 is really, since 1 times 10 to the 11th is so big, adding just 5,324 doesn't really change it. So I'm just going to keep that it's pretty much 1.0 times 10 to the 11th. It's such a big number. It didn't change that at all. It's equal to negative x. So to find x, we just need to divide by negative 1 to get x equals negative 1.0 times 10 to the 11th. All right, so that's for our that's for this guy. That's telling me that that's for 1 mole of that substance. Now, this is telling me that negative 1.0 times 10 to the 11th kilojoules for every 1 mole of C8H18. So now we just have a little bit of mole mapping to do, or moles to grams. We need to do on our calculator, figure out what the molar mass of C8H18 is. So 8 times 12, the molar mass of carbon is 12, so 12 times 8 is 96 plus 18, because there's 18 hydrogens. So let's say 1 mole of octane has a molar mass of 114 grams. And we're almost there. This is for grams. We want kilograms. So let's do 1 more grams to kilograms. Make sure that our grams and grams are diagonal from each other. 1 kilogram is 1,000 grams. So we're going to take that, negative 1 times 10 to the 11th. Oops. Negative 1 times 10 to the 11th, times it by 1,000, and divide it by 114. Oops, 114. Ah, darn it. So doing that reaction, or the math to get to that reaction, I dropped the negative just because, yes, X is telling me that it's an exothermic, 1 times 10 to the 11th. So I just dropped that negative because when we're going from moles to grams and grams to kilograms, we don't care about the exo versus endothermic. So when we do the math, we get 8.77 times 10 to the 11th kilograms of octane. But really, there's a bigger story here. We really looked at this problem. We were given the delta H as opposed to finding the delta H like we did the last couple of times. We knew all but 1 of the enthalpies of formation. So essentially what we did was we knew our products and we knew all but 1 of the reactants. So we just had this as our target finding. Really, this problem wasn't the best worded because they gave us such large numbers the algebra kind of fell apart here. I mean, we had such a large number that by adding all of our product to it, didn't even change it that much. So not the best, but at least you got the hang of, you know where to go. If you're given heat, and we knew all but one, we're just throwing in a variable to find, which we should be able to do. And then once we find it, we can go from moles to grams, and if asked, grams to kilograms. Let's look at another example where it wants us to calculate delta H for decomposing 10 grams of limestone calcium carbonate under standard conditions. And it gives us the equation here. And what's great is they gave us the standard enthalpies of formation, so we don't have to even look those up. So we're going to do my products minus my reactants. So I've got my CaO, my negative 634.9, and there's only one of those. And oxygen, of course, is 0. So negative 634.9. I'm going to do that's my products, minus my reactants, my calcium carbonate, which is negative 1207.6. So let's do that to see what our delta H is. Negative 634.9 minus a negative 1207.6. So my delta H is 572.7. And that is for every 1 mole of calcium carbonate. But I don't have 1 mole of calcium carbonate, or at least I don't think I have 1 mole. I have 10 grams of calcium carbonate. So I'm just going to do 10 grams of CaCO3. I need to figure out how many moles of CaCO3 that is. So by looking at a periodic table, I can do oxygen's mass, which is 16, times that by 3, because I've got 3 of them. Add a carbon, which is 12, and add a calcium, which is 40. So I have a molar mass of 100 grams calcium carbonate for 1 mole. So let's do 10 divided by 100 to get 0.1 moles of calcium carbonate. Well, I know how many kilojoules for 1 mole, so let's figure out how many kilojoules of energy for 0.1 moles. So I'm going to do that 0.1 times 572.7. And I should get 57.27 positive endothermic, positive 57.27 kilojoules of heat, of energy, will be my delta H. So if you go back to think about it, my calcium carbonate, this decomposition reaction, it takes energy to break these bonds, to break them down into what they're made of, and it takes, so this one specifically took 57.27 kilojoules of energy to break apart this. So this is an endothermic reaction. We know endothermic breaks bonds. And again, I took my products minus my reactants to get that delta H, and that was for 1 mole of calcium carbonate. We only had 10 grams, so we figured out 10 grams to moles, so we only had 0.1 moles. So by taking that per mole and multiplying it by 0.1 moles so that these moles are diagonal from one another and cancel out, I can find out how much energy was required to break apart 10 grams of that substance. Lastly, we're going to talk about bond energies. So chemical reactions involve breaking bonds in reactant molecules and making new bonds to create those products. The delta H, the enthalpy of the reaction, can be estimated by comparing the cost of breaking old bonds to the income from making new bonds. The amount of energy it takes to break 1 mole of a bond in a compound is called the bond energy. The actual bond energy depends on the surrounding atoms and other factors, and we often use an average bond energy to estimate that delta H of the reaction. Bond breaking is endothermic. Bond making is exothermic. So, for example, we would just look up what these average bond energies are. So to break a hydrogen-hydrogen bond, we would see that it takes 435 kilojoules of energy. To break a carbon-carbon double bond, it takes 837 kilojoules of energy. Remember, to break bonds, bond breaking is endothermic. That's a positive value. So all of these bond breakings, all of these, and we would, again, just look them up. To break a bromine-bromine bond is an average of about 193 kilojoules for 1 mole. So endothermic, this is really important. Endothermic, bonds breaking, positive. Exothermic means bond making, and it releases. So to find that delta H, we sum up the bonds broken, which is our, if they're breaking, it's endothermic, and our bonds formed, which is exothermic, and if bonds are formed, this is going to be in our products. Bonds that are broken, we're breaking apart those reactants to form these products, exothermic. Let's look at an example problem. Oops, I guess we have one more thing before we do our example problem. Looking at trends. So in general, the more electrons two atoms share, the stronger that covalent bond. So if I had a triple bonded carbon, notice the amount of energy needed to break that 837 versus a double bonded is only 600. So it takes more energy, the more bonds there are, is harder to break apart. Think of it that way. Triple bond is harder to break than a double bond. Double bond is harder to break than a single bond at 347. Same if we look at carbon triple bonded to nitrogen versus double versus single. Almost 900 to 600 to 300. Also, we can look at, similarly, when we were looking at halogens, where I have fluorine and then chlorine and bromine and iodine. Bromine to fluorine has a higher amount of energy needed to break it than bromine to chlorine. So bonds get weaker as we go down the column. So similar, as we go up, they get stronger. So bromine to fluorine is stronger than bromine to chlorine, which is stronger than bromine to bromine. As we go down, those atoms get bigger, and so easier to break that bond. The shorter the covalent bond, so as you get higher up here, more electronegative, there's a greater pull. This is a shorter bond, so they're stronger. It's going to take more energy to break that. So, but they get weaker as you go down a column. They get stronger as you go across a period. So here's an example where I've got methane, this is CH4 plus Cl2 chlorine to give me CH3Cl plus HCl. So if we look at bonds, my reactants, so let's look at bonds breaking. We have to break this, we have to break this in order to form these new ones. So we would look at that table and look at how much energy does it take to break C and H. And so we look at C and H and it takes 414. 414 kilojoules to break that CH. We also need to break that chlorine-chlorine bond. So we need to find chlorine-chlorine. Where is ClCl? I'm not seeing it on there. Cl. Oh, there we go. 243 kilojoules. So if I look at the two bond breakings and add them up, I get 657 kilojoules of energy to break it. But I'm also making two bonds. I'm making a carbon-chlorine bond, and I'm making a hydrogen and chlorine bond. So I need to look at, to make those, again, making those is an exothermic reaction. So 339 kilojoules and 431 kilojoules. And again, I can get that right from here. CCl, 339, no, but we're not making these. We're breaking, or I'm sorry, we're not breaking them, we're making them. So it's just going to be the opposite sign. So negative 339. And to create chlorine and hydrogen is 431. But again, that's negative. So we need to add these up to get negative 770. And then I just need to find my delta heat of my reaction. I need to do my reactants, my products. So bonds broken, 615 kilojoules. Bonds made, negative 770. Add them together. So the delta H of this reaction is negative 113 kilojoules. So we can see that overall this reaction is an exothermic reaction. So we've got our bonds breaking. This is our endo. Remember, and that is our reactants. This is our positive. And we're looking at our exothermic, our reactants, our products, which is exo, which is negative. And when I look at my overall heat of reaction, looking at my reactants that are breaking, my products that are making, my overall heat of reaction is exothermic. And to look at this as a picture, what we just did, again, we were breaking these two bonds for my reactants. So that took energy. We can see that this is showing how much energy 4, 5, 6, what was it, 707 something, 4, 5, 6, no, 657 kilojoules. We can see how much energy it took to break those bonds. And then to make those two bonds in the products, we can see how much energy was released. And this is our net delta H for the reaction. It's just showing the difference between the two. This is how much energy it took to break. This is how much energy it took to make. This is my overall delta H. All right, you are doing awesome. We have 2 more practice problems and then we are done with this module. So let's look at this and calculate the heat change, delta H, for the formation of nitrogen monoxide from its elements. Let's write the target balanced equation here. So we want to form nitrogen monoxide. And the elements that make it up, N2 plus O2. Okay, but we're not balanced. I want 1 mole of nitrogen monoxide. So I can't just put a 2 right here in front of it. That would give me 2 moles. So let's use our fractions and say we'll use half of an oxygen, half of a nitrogen. So that gives me half of 2, N2 is 1 N and 1 O to give me NO. Great. Now let's look at our 2 elementary equations. 1 2. All right, first let's look to see where nitrogen is, just because we have it listed first. Nitrogen, nitrogen, not there, but nitrogen is listed in our first elementary one, and there's 2 nitrogens. Well, so the first problem is it's on the right side of the arrow. I want my nitrogen on the left side of the arrow, so at least we need to flip it. Also, I want half, I don't want 2, so how do I get 2 down to half? Well, I could divide it by 4, right? Because that would make this 2/4, which is 1/2. So let's do that and divide everything by 4. So let's flip this. So I'm going to write 2/4 of N2 plus, I got 6 divided by 4 of H2O. So I'll just write 6/4 of H2O. This one, NH3, again, I'm going to divide it by 4. So let's just write NH3 because 4 divided by 4 is 1. And 3/4 of oxygen. So here, I'm going to need to flip this and divide by 4. So that gives me my delta H of negative 1530 will become positive 1530. And I'm going to divide that by 4. My delta H is 382.5, and that's a positive. Okay, so that gives me my 1/2 nitrogen on the left, because 2/4 is 1/2. Oxygen is in both of them, so I'm just going to hang on tight for just a second, but I do want NO, and which of these, where is NO unique? Right there. So what's nice is in my second, so this is my first equation rewritten, it is in my second, and it is on the right, which is great. But here I have 4 NOs, and I only want 1 NO. So I can get there by just dividing everything by 4. So let's rewrite this as is, but everything is divided by 4. So I'm going to write, instead of 4 NH3s, it's going to be 1 NH3. Instead of 5 oxygens, we're going to do 5 divided by 4, 5/4 oxygen. 4 NOs divided by 4 is just 1 NO. 6 waters divided by 4, we'll just say 6/4 H2O. And then let's check my delta H. I kept the sign the same, all I did was divide it by 4. So negative 1170 divided by 4. So my new delta H is negative 292.5 kilojoules. All right, let's look to see, make sure that everything cancels out to give me my target equation. Well, I can see right off the bat I saw that I have an NH3 on the right and an NH3 on the left, which means that we can cancel those babies out. You can also see that on the left I have 6/4 H2O and a 6/4 H2O. Get rid of those. All right, so now let's see what we have unique. I have no other N2s on the right over here. Well, I'm going to say that that is going to come down here. So 2/4 N2, which I'm just going to reduce and say 1/2 N2 plus, I want half of an oxygen. Right here I have 5/4 of an oxygen. Over here I have 3/4 of an oxygen. So let's simplify that. If I get rid of 3/4 and I subtract that over here, 5/4 minus 3/4 is equal to 2/4. And 2/4 is the same thing as 1/2. And then the only thing left on my right side is NO. So yes, we got the target equation. So that just means I need to add these 2 delta H's up. And if I did my negative 292.5 plus 382.5, I should get a delta H of 90 kilojoules. And that is a positive number. So this is an endothermic reaction. Okay, let's look at this other one. Looking at the enthalpy change for this reaction. So this is my target, and these are my elementary reactions. So let's figure out where my P4O6 is. I want it on the left, and right here it's on the right. What's great is that I want 1 mole of it, and there is already 1 mole of it. So all I need to do is take my first reaction and flip it. So let's rewrite that. I will then have P4O6 and then have P4 on the right, or I'm sorry, yep, P4 on the right plus 3 O2s. Then all I needed to do for my delta H here is flip the sign. So it becomes a positive 1640.1 kilojoules. So then I got that covered. Now let's look and find 2 O2s. Well, I got several O2s, so I'm just going to move on to the next one. I need P4O10 on the right. And if we see this, I actually have P4O10 on the right. So we're just going to leave this alone. And let's see what we have. P4 plus 5 O2s, P4O10. And if we leave that first one alone, negative 2940.1 kilojoules. So let's see if this works out. I've got my P4O6 on the left, P4O6. Good, I've got no other P4O6. On the right I have a P4 and on the left I have a P4, so those can cancel out. That's great. On the right I have 3 O2s. On the left I have 5 O2s. So let's subtract these 3 O2s, get rid of them. 5 minus 3 would give me 2 O2s. So that keeps this, that becomes a 3. And then the only thing left on the right is my P4O10. That's great. So now we just need to sum up our delta H's. So we have 1640.1 plus a negative 2940.1. And my delta H for this reaction is negative 1300 kilojoules. Again, another exothermic reaction. Okay, the last one, my printer kind of pooped out here, so I just wrote it. We need to calculate the enthalpy change for this reaction, given these 2 elementary reactions. So if I look at this and go, all right, I need my IF5 on the left. So where is IF5? It is in my second reaction, and it's on, I like that there's 1 mole of each, but it's on the wrong side. So let's rewrite reaction number 2 by flipping this reaction. So I would say IF5 yields IF plus 2F. And that means that delta H is going to be positive 745 kilojoules. Okay, that's great. Now we need IF3 on the right-hand side. And I have IF3 on the right. So let's try leaving this alone. Sorry, I forgot a 2 here and a 2 here. But so I flipped this bottom one. So I have IF5 yields IF plus 2 F2s. I like that my IF3 is on the right side of this arrow and it's on the right side of this arrow. So let's try leaving number 1 alone. IF plus F2 yields IF3. My delta H stays the same, negative 390 kilojoules. Let's see if this works out. So on the left side, I have an IF, and on the right side of my arrow, I have an IF. So those are going to cancel. On the left side, I have an F2. On my right side, I have 2 F2s. So that 1 F2 is going to go away, and it's going to leave me with, so I'm going to subtract 1 F2, get rid of 1 F2. That leaves me with just 1. So now I can say the only thing on the left side of that arrow is IF5. On the right side, I have an IF3, and I have one F2. Great. So now we just need to add up our delta H's, negative 390 plus 745, for a delta H of 355, a positive value, showing that this overall is an endothermic reaction.